Welcome to Analytic Methods for Lawyers. I'm Professor Seth Chandler at the University of Houston Law Center, and this video is a companion to an essay providing an overview of the course that we'll be going through together. This computational essay will give you a flavor of what you're going to learn in the course. Now, both this essay and the lecture may be a little bit terrifying. It's intended for law students, and you may think as a law student, I could never learn this, but you can, and you will. It's going to take some work on your part. Learning always does. It wasn't easy to learn constitutional law. It wasn't easy to learn secured transactions. It wasn't easy to learn immigration law, but I'm going to encourage you to learn by doing and by having some interim assessments designed to make sure you don't try to cram it all in at the end and don't get off the track. By the end of this course, though, you're going to have much greater fluency in the exploding technical world that surrounds lawyers, be that in your own business of legal practice or in looking at evidence. It's not quite going to give you the joint degree in computer science and law that the former CFO of Goldman Sachs, Martin Chavez, calls a winning combination that'll keep you busy for a long time. But I'm going to try and come close. So, in the future, when a machine learning algorithm appears to be discriminating against your client, or more likely, when someone accuses your perfectly innocent client of having designed or having deployed a machine learning algorithm that's allegedly injured someone, you'll have some idea what the parties are really arguing about and what questions need to be asked and answered in order to resolve the dispute in an advantageous, yet just fashion. We're going to spend some time on the new fields of XAI, which means explainable artificial intelligence, and adversarial methods. You're going to get to see inside the black box of many machine learning algorithms, or try to do so and see some of the problems with attempting to get inside that box. You're going to see how the vulnerabilities of machine learning can be exploited by creating what I like to think of as the equivalent of optical illusions that the machine will systematically misunderstand. You'll understand common techniques of statistics, not in the way some of you may have been taught by punching numbers into a TI-83 calculator or getting an Excel spreadsheet to perform one of its pre-trained tricks or memorizing complex formulas. Rather, I want you to understand what's really going on behind the analysis and whether the statistical tools that are being deployed are appropriate or ways of framing the matter that, just like good legal argument, buries assumption and attempts to persuade on a more subtle and subliminal basis. You're going to have an understanding of several other fields as well. We're going to spend some time understanding the distinction between association and causation. In recent years, a field called Causal Inference has evolved that permits some tentative causal hypotheses to evolve, even from data where a direct proof of causation isn't possible. And you'll be able to make an assessment as to whether someone who claims causation, which we know is a crucial concept in much of the law, is making a credible assertion. And if they're not, how you can go about challenging the causal claim. We're going to spend some time on computational linguistics. There's already rudimentary versions of computational linguistics that are ubiquitous in legal practice. That's what e-discovery is all about. But future developments really promise to do much more, maybe threaten to do much more, and revolutionize the practice of law. For example, right now, there are programs that can take a hand-drawn sketch and turn it into a much more elaborate painting. There are programs that can take visual or musical art created in one style and change it into another in a way that's really quite artful. What if you could use those same techniques on prose? No, we're not quite there yet. Don't abandon your legal writing course yet. It turns out human language is astonishingly complex, but we're going to see tools such as GPT-3 and others that are beginning down this path and making some progress. Other areas we're going to try to touch on include cryptography, such as blockchain and other forms of cryptography, networks, and a little bit of finance. And there's another skill you're going to learn in this course, and for some it might be the most important skill, for others perhaps not important. You're going to gain at least a reading knowledge of a computer programming language. In the modern world, if you really want to know why something has occurred the way it has, the answer probably doesn't lie in the fuzzy intent of some human thinker, but actually in some algorithm, written in a computer language by somebody, some person who had to make those fuzzy thoughts concrete. And that assertion, I think, holds true for government regulations. Just look at how things like the Affordable Care Act are being implemented, corporate policies, look at how hiring works, political speech, think about how Twitter, Facebook, and other algorithms prioritize content. And so at some point, you're likely to need to know the details. Now, of course, you can't learn every computer language in which fuzzy human thoughts are encoded. You can't learn C, C++, Java, Go, Rust, Swift, JavaScript, Python, R, MATLAB, Groovy, Julia, or legacy languages such as Visual Basic, PHP, SQL, or Perl. You're going to have to rely on other people to help you. But by learning a particular computer language, here Wolfram language, you're going to gain some sensitivity to some of the fairly universal concepts of computer languages, such as the importance of precise syntax, ideas of functional programming, ideas of object-oriented programming, pattern matching, modularization, encapsulation. Now, there are some definite disadvantages of relying heavily on Wolfram language. It's not a hugely popular language, and its heavy use of pattern matching and functional construct may require some experienced programmers among you to refactor various concepts. There's a steep learning curve to go up at the beginning, and it's not open source or free in the real world. But I use Wolfram language for a variety of reasons. First off, it's an immensely expressive language. It's sort of like English. You almost kind of speak it. And what having a large language does is it permits very terse programs to be written. I mean, imagine how long it would take you to explain something in detail if you only had 1,000 words. With Wolfram language, you've got thousands of words that are well-defined and documented, and that permits you, once you have the vocabulary, to write very short programs that are understandable. And because programs tend to have bugs in proportion to the number of lines, it also reduces the probability of error. It has immensely powerful integrated libraries, so you don't have to be searching out which library works and who it comes from, and the libraries use inconsistent vocabulary, and they don't play well with other libraries, and there are unannounced version changes. They don't really care about backward compatibility that often. Wolfram language, powerful, integrated, backward compatible libraries that mean that programs that I and others wrote in 2005 still work. Okay? It facilitates symbolic programming, such as algebra and calculus, in ways that are different than in most other languages, so that you don't have to plug in numbers. It's not like a spreadsheet. You can actually tell it, here's some algebraic thing, solve for X. It also lets you write programs that write programs, and programs that write programs that write programs. That's a very important capability. It's spectacularly good at visualization and interactive visualization, and I'm very much of a visual learner myself, and so you're going to see a lot of pictures in this class, and Wolfram language makes very pretty pictures, and it's good at producing them. The notebook interface, basically what you're going to see in this essay and video is a mixture of prose and code. That's now called literate programming, or sometimes called a computational essay. And Wolfram language has been doing this for years, and it's good at it. Speaking of years, it's been around for 30 years. It's not a flash-in-the-pan language. It's lasted, and I anticipate that it will last for quite some time. And frankly, the final reason is I know it real well, and so that lets me fluently communicate in it and permits us to cover a lot of ground. So, finally, this essay and this video I'm not just going to tell you what we're going to learn in this course, but also I'm going to kind of demonstrate how we're going to learn. That is, this essay is illustrative of what I'm going to do in the course. Yes, there's some outside reading, not nearly as much as in most of your classes. And there are some brief exercises that I strongly suggest you perform, because I think learning in this area is really learning by doing. But mostly we're going to learn through a series of essays authored by me and accompanying videos made by me. So you're not going to see the code as something hidden away, but it's more like documentation. You can kind of think of the code as footnotes or citations in a legal essay. Like, the purpose of footnotes is basically to document how did you reach that conclusion? What's the reasoning process by which you reach that conclusion? And that's essentially the function of code in these essays. It's to show you very precisely how the result I'm putting forward was achieved. So it's testable. And it also means it's modifiable in actually a way that legal research is not so modifiable if it's done properly. What's nice about Wolfram language is the code tends to be short. Not always. There are things that are, just really complicated. But you're going to see code that's quite short so that when I include it in the essay, it's not terribly distracting, at least once you get used to it. The essays and the videos for this course are, I think, actually going to be a lot like this. Now, in those other essays, I'm going to dive deeper into various details. And I'm going to really try hard to create a linear sequence out of the seamless web of analytic methods. This is basically the problem. It's the same problem as teaching law, where if you don't understand civil procedure, it's very hard to understand what's going on in a contracts case. And if you don't understand contracts, it can be hard to understand property, but property in turn relies on the Constitution. And so there are a lot of concepts that are woven together, but we can't throw them at you all at once. Now, the downside of that, this is a warning, is that does mean there's a front-loaded slog that is starting right now where we get some of the basics under our belt. Some of the initial videos and essays are long. This one I suspect I haven't finished giving it yet, but I'm guessing it's going to be over an hour. And I know some of the other early videos are over an hour. Nobody can watch an hour-long, intense video, at least no one I know. So rather than just artificially break them up into 15 to 20-minute chunks, I'm going to let you decide how to break up the viewing. This course, I'm putting it out in the open, and I'm making it available to anyone. What do you get for enrolling in the class? After all, you paid a lot of money for it. You get the benefit of interacting with me in person, or during this COVID semester, virtually via Zoom. There's no obligation to ever meet with me for office hours. But, I'm working hard to make this as clear as I can. I'm not perfect, and some of this material is frankly difficult. So if you don't understand material that's being presented, come meet me during office hours, or if those particular times aren't good for you, contact me and we'll work out something. My goal is to not have you be scared. Okay? There's nothing really any more scary about this course than about property law. And the other thing I would urge you to do, you don't have to, there's a final exam if you'd prefer to take that. But if you're finding the materials interesting, I would suggest you find a project to do and work on with me. Really, I do feel that this is an area where you learn the most by actually trying to get things done. The advantage of is like being able to create a computer program, particularly one that relates to law, is kind of a superpower. And this course is going to give you an opportunity to develop that superpower. So, without further ado, let's begin. I'm going to start with some statistics. Basically, what we're going to do here is import some data on student characteristics, their grades, and use linear regression to see if we can find some associations between those characteristics and the grades. So I'm going to import the file that contains the grade data. There we go. You can see it has lots of stuff. I'm going to fiddle with it because I'm not really interested in the interim grades in columns G1 and G2. I just want their final grade. Okay. And now I'm going to do a linear regression. These are simply all the variables that we're going to be looking at. This is code that's going to tell the computer that some of these variables are categorical, they're not numbers. So we do that, and we're done. And now we can start to look at the parameters that we find of our regression estimate. And we're going to see, for example, that gender does appear to matter. At least there's an association. That does not mean causation. Family status might matter, but it's not statistically significant. In any event, we can go through all of these factors and take a look at what seems to matter and what doesn't. And then we can also take a look at whether our model actually explains much of the previously unexplained variation in the rates, the student grades. And we're going to learn that that's really not a very good model. Not terrible, but not very good. So just an example of the kind of thing we'll learn with statistics. We're going to learn about visualizations. We're going to learn about how to make a good graphic. Here's actually an animation that I constructed that has to do with the operation of the tort system and whether the negligence standard, strict liability, or something in between is either efficient or most likely to prevent accidents, as well as the relationship of activity to the legal standard. So that's one of the kind of things we'll learn how to construct and why it's either good or not so good. We're also going to take a look at bad graphics. And this graphic has been called the worst graphic ever made. They might be right, and we'll discuss why it is so absolutely dreadful. Well, what about machine learning? This is a very, very hot area right now, and we're going to learn about some concepts of machine learning, such as the advisability of separating training and testing data sets, as well as the role of validation data sets. And we're going to learn about various flavors of machine learning, such as supervised learning, unsupervised learning, generative methods, a few others. We're not going to study reinforcement learning, so if that was your big desire to take this course, sorry. So let's actually take our same data on the students, and I want to scramble them just to make sure that if they were in any order when they came out of the data set, they're not in order anymore. And I'm going to split them up into a training data set that we're going to use to form our model, and then a test data set. That's data that was never seen during the training process, and it simulates how our model is going to perform when it sees data that it's never seen before. So we split it up. There we go. We're basically ready to roll. I'm going to be using predict, which is, generally speaking, a form of AutoML that does an awful lot of the work that otherwise would need to be done by hand. Ordinarily, predict will select the machine learning algorithm it likes. It might think that decision trees are appropriate, or nearest neighbors, random forests, neural networks. Here, however, just for pedagogic purposes, I am going to force it to use something called a random forest, which we will learn about. By the way, this is an error message here, and it's only here as it's a residue of some previous work I was doing, but now you know what an error message looks like. But I don't think when I actually run this now, that's going to exist. And it is thinking, and it did it. That little blinky you saw, that was it actually doing the computation, because this is actually a fairly simple data set. Now what I want to do is I want to see, well, how does this model that we built, which I've labeled pre, perform when it sees data that it's never seen before? Okay, so let's run that. And you're going to see various statistics associated with it, including that R squared, which is at 0.171, is suggesting that it's not performing so great when it sees new data. And in fact, one of the criticisms that people have of traditional statistics is that that R squared value that I showed you earlier is really an example of something called overfitting that we will discuss, and it's a very misleading estimate of if you want to use that linear function in the future, it's not going to give you as good performance as you might think. And so in many ways, the machine learning method of doing this is actually probably a superior form of if you want to build a predictive model. Okay, so we're going to spend a good deal of time in this course on neural networks. They have been sort of the star of the modern machine learning world. Partly that's because they're a good idea, and partly because, as it happens, the methods they use align very well with contemporary computer architectures. It's sort of actually a happy confluence that the same kind of computations you need to do in gaming, which is a giant market, are actually very similar to the computations that you tend to do in a lot of neural networks, and so we have very good hardware for doing it. All right, so let's start with something. This is a what's the right term? It's a simple example. You would never use a neural network of the complexity I'm about to have, I think, in order to perform a relatively simple task like this. But let's look at the Titanic data set, okay? So here we go. I load it in. It's got a bunch of people. We know what cabin class they were in, what age they were on, what their sex or gender was, and whether they survived. We've got 1,309 of these people. I can scroll through them. Now, actually, what you're going to find is often the hardest part of machine learning is not the machine learning part. It's getting the data exactly right. And so I'm not going to teach you details of what's sometimes called data munging, but I am going to make you aware of the issue. Certainly if you do a project, I'm willing to bet you're going to spend some time on data munging. And you ought to, when you see a result of machine learning or statistics out in the real world, you ought to check how that data was massaged, because if I have the ability to massage the data before it ever hits my algorithm, I can do very many fun things and tend to get results that favor my advocacy position. Okay, so among the munging things I want to do is I really don't like the use of the word class as a column name, because class in machine learning has a very special meaning that has nothing to do with how you traveled on the Titanic. And so I'm just going to substitute in cabin for it. Also, just for reasons that need not detain us, I want to use survived and died rather than true and false as what I'm trying to predict. And I also want to change the form of the data a little bit. So instead of being column-oriented data, it's row-oriented data, in which we have these 4 categories, and then we have all the instances. I also want to delete those rows for now, in which some of the data is missing, like maybe we don't know the person's age. In an ideal world, I might spend some time trying to impute missing values. There's a whole art form of missing value imputation. I don't want to do it here, so I'm just going to get rid of it. All right. So we now have Titanic T, which is the data in a different form. And again, I'm going to split that up into training and test sets. So now for cabin, I have training data, 700 examples. And then I'm going to test how my model performs on 346 of the remaining data items. I've got the same thing for age, sex, and survival. Let's build that neural network to find out who lives, who dies. In the course of doing this, I'm going to try and teach you a little bit about neural networks. Obviously, there's a huge amount of detail that we'll go into later. But you need to understand that neural networks have what are called layers. And you can really think of a layer as just a function. It's generally a pretty powerful function, and it's optimized to execute on a computer in special ways, but at bottom, it's just a function, and a neural network is roughly just a list of composed functions. Okay, so here I'm going to designate basically what types of functions I'm going to use, and I'm going to give them names. Like I'm going to call catenate a catenate layer. I'm going to call L5 this particular linear layer. I'm going to call my loss a cross entropy loss layer. So all I'm doing is basically saying, here are the toys in my toy chest that I'm going to play with in this neural network, and here are the names that I'm going to give my little stuffed animals here. Okay, Now, I got to hook them all up. I've got to tell the computer how the data flows into each layer and where it goes when it comes out of the layer. And it can come in from more than one place, and it can go out from more than one place through various ports. So I'm going to specify the edges. And finally, I got to tell the computer a little bit about what kind of information is coming in, what's the form of the information coming in, and what's the form of the information going out. So I do that here. And now, the hard stuff's done. Now I just put it all together. And I look for spelling errors. So let's remember to execute some code here. See, this is blue. Blue means I haven't executed the code. It's just text at this point. It's not in the kernel as actual code. So come on. There we go. Okay. And now I'm going to put it all together. I put the nodes, the edges, and the port specifications together. Don't worry about that sequence hiding behind the curtain there. All right, we can take a look at a picture of this network. Often this is very helpful. I know it's a little inscrutable, but you can see various things, sex, cabin, age, coming into the network. These are little probes I created. Normally I wouldn't do this if I weren't sort of in a teaching mode, but if I want to see what's going on, we have to have little probes in here. And here are various layers of the network. That's sort of a schematic or an icon for a softmax layer. And here's what's coming out. We're going to have output coming out and probabilities coming out. Just so you know, what I've given is a very high-level sort of abstract description of the network, and what actually ends up happening is the network gets compiled down to a more hardware-oriented understanding of the network. So I've built a structure now for analyzing data, but it hasn't done any work yet. It just sort of exists. And the idea of supervised learning is to throw data at that structure, have it adjust itself in response to the data that's been thrown at it, so that at the end of my throwing fit, it actually has magically reformed itself so that when I give it future data, it will give me the answer that I want. That is, it will predict, in this instance, how a student is going to fare when I throw at it information about whether they're having a romance, whether their family is stable, etc. Okay? And so this is the idea of supervised learning. You have a structure, you throw data at it, the machine adjusts itself because it says, oh, I made a mistake. I need to fix something that I'm doing. Or I got it right. I think I'll do more of that. Ultimately, though, and let's actually, I guess, watch that. Let's watch that process. Okay. So here's what it looks like. The command involved is nettrain. Here's my data. I'm telling you what loss function I'm using. This is just a bunch of stuff. All right, and I'm only going to do 100 training rounds. This is, again, just for pedagogic purposes. I could go longer, although basically this data set is easy enough that going much longer wouldn't help much anyway. So here we go. All right, and it's computing away, and actually it's done. I guess that didn't take long at all. I'll teach you what all this squiggly stuff means, what all this stuff means. But for now, just know it did it. It is now a trained neural network. Our trained object, it's an object that has lots of properties. If I want to see what does the trained net look like, I can execute this code, see a little picture of what's going on. It really doesn't look much different than my initial picture, except now there are like lots of numbers inside here that are actually optimized to produce good predictions of output and probability. So now I want to see how did I do. How is my neural network, which was just trained on some of the Titanic data, going to do when it confronts further passengers? And so I'm going to take my trained net, take my data, and here are some of the stats I want. And I'm going to teach you what all these stats mean. Right now, they may seem totally inscrutable, like what's a Cohen kappa? But by the time you're done with this course, it's not really any different from understanding batting average or free throw percentage or time of possession. Just numbers. So here we go. And we can see answers. And by the way, just so you know, we're getting 80% right, or 79, on data it's never seen before. And actually, that's pretty decent. That's a Cohen kappa of 57%. All right, and lots of other stuff too. So one other thing we can do is we can actually look at what's going on inside the network. Just so you, I'm going to try and break into the black box here. So let's get some data. Actually, this little chunk of code is unnecessary. Let's delete it. And we're going to do this interactively. Basically, what we're seeing here is how the data flows through the network. Like we could start here, where we're going to represent the data with 15 pieces of data. You can see there's certain clusterings going on. We're going to apply a nonlinearity. That's going to change the representation of the data, have it flow through some more. Now we've simplified it down to 5. Another nonlinearity. And finally, we're going to come out with some probabilities. And these are actually the various probabilities. And this is the probability. I forget if this is dying or surviving, but you can see it's the opposite here. Whatever it was here, it's 1 minus that over there. And you can see some clustering. You know, maybe these are the women and children who are most likely to survive, at least according to the story. And maybe these are the third-class older men who might not have fared so well on the Titanic. Let's turn to a different area we're going to cover in this course, which is computational linguistics. And I want to divide the discussion into two areas. The first are old school methods, and the second are newer school methods. So let's look at some old school methods. Let's start by getting the Constitution, bringing that in. There it is, we the people, blah, blah, blah. We're going to break it up into sentences using a little AI that figures out what sentence breaks are. And just for convenience, I'm going to make everything lowercase so we don't have to worry about words being different depending on whether they were at the beginning of a sentence or not. So we do that, and we've got our sentences. How many of them are there? Well, they think there are 283. What I'm now going to do is I'm going to use something called Idf Analysis, which is a method which basically says the signature of a sentence or a phrase is the frequency with which it uses unusual words. That's one way of sort of identifying, like if a sentence has the in it, or made, or cat, or something, really doesn't help us tell one sentence from another. On the other hand, if the sentence has anathema, or calibrate, or some other fancier word, that might be a better indication of what it's about, particularly if calibrate and etc. aren't used very much in the document. So we're going to use a high-level function in Wolfram language called feature extract to take our Constitution sentences, and we're going to use the TF-IDF method to do so. All right, so we're done. Now what we're going to do is we're going to tell the computer, hey, when you get a sentence, I want you to figure out which sentences in the Constitution are closest to that. So here's our little code to do that. And let's look at Constitution sentence 48. If any bill shall not be returned, so this is basically the pocket veto. And let's see if we can figure out which sentences in the Constitution are closest to that. And you can see immediately the application for this. Basically, this is natural language search that you see in Westlaw Lexis, and I'm sure I sure hope they've done fancier things than I did here in 3 minutes, but conceptually, it's very similar. So we do it, and the first thing it finds is the first sentence. The second thing it finds is the actual regular veto provision. And then the third thing it finds is basically how a bill becomes law and the veto override provision. So our little cheesy, made in 3 minutes Constitution finder actually in this instance did pretty darn well. Now I'm going to write a function called generateSample that takes a language model, like this thing here. It takes some input, which is a string. I'm going to tell it how many more words do I want to produce, and then there's something called the temperature. All right? So here we go. And here's the beginning of a sentence. There must be more than merely preparatory acts, and let's see how it would complete it. There must be more than merely preparatory acts and preparations, for these provisions must also be kept out of acts of union and by careful pleading with the. So it's not great. Let's try GPT-2 on this one. This computational essay will give you a flavor of, how does it complete it, of why Apple Pass and other white hat crowd kits stand out as possible fourth generation hardware-based cryptocurrencies. I've certainly read prose that is less jargon-laden and less sensible than that, so here I would call that a success. And actually, we're now not on GPT-2, which at the time was called Technology Too Dangerous to be Released, although they later changed their mind. We're now up to GPT-3 and various other competitors that really do, as I'll show you later in the course, a phenomenal job of sounding pretty human. And so you might think about applications for this sort of text completion and text recognition technology. So, some of you may be familiar with the case of Martin versus Hunter's Lessee. It involves the ability of the Supreme Court to interpret the Constitution in a fashion contrary to that of the way that state courts had interpreted it. And it's involved land, actually, in which Chief Justice Marshall had a major financial interest. And so he formally recused himself in the case. But if you read the opinion of Justice Story, to some ears, it has a somewhat similar writing style than that of Justice Marshall, and so suspicious minds might wonder whether Justice Marshall might have ghostwritten portions, at least, of the opinion. So let's see if modern computer science can provide any light on that. And here, this is the one part of the code that it's going to be dormant. I'm just basically going to be copying stuff that I did in version 12.1.1 of Wolfram. Okay, so I import the case, which I downloaded from Westlaw. I now split it into sentences to do a little formatting. This is the munging part again. And you can see that it's split up into various sentences. So that's my Marshall data set. It's obviously Chief Justice Marshall wrote many, many opinions, and one of the issues with this particular little study is I'm only picking one of them. Let's pick one of Justice Story's opinions. It's Prigg versus Pennsylvania about the Fugitive Slave Clause. And we import it, do the same thing, munge, split it up into sentences, and we've got this issue of whether taking a slave back was kidnapping or whether it was just rightful repatriation of a slave. So let's now put the data together. Let's jumble it all up so it's not obvious which one came from which justice. Again, I'm going to split it into training and test sets. And so now what we have is we have a list of sentences, and for each sentence it's going to tell us who wrote it. Story wrote this one, Marshall wrote this one, Story wrote this one, etc. So in what we want to do is to figure out a way to take that language, maybe turn it into some numbers, and then say those numbers are associated with Story or Marshall or Story, and then use that same function on text the machine has never seen before, and it will be able to figure out, oh, this looks like a Marshall sentence, this looks like a Story sentence. And we can run that machine against the case that I'm particularly interested in, Martin versus Hunter's Lessee, and see whether it thinks Marshall or Story wrote the opinion. All right, so the particular neural net I'm going to use for this is actually not very simple. It's a simpler one than exist, and I simply used it because this is sort of a toy model, and I just wanted things to go quickly. It's a species of BERT. So there's our BERT. And I'm going to again split the BERT wants words, it wants lists of words, it doesn't want whole sentences. So we'll turn it into words, get the data in the right format. And so now you can now think of each sentence of an opinion as being like a picture in which here are the 256 attributes of each word in the sentence. And as you may have noticed, Justice Marshall tended to write really long sentences. So here are the 179 words of the sentence, and this is a picture of what it looks like. And just as you may have seen that modern neural networks can look at a picture of a pig and say that's a pig, and look at a picture of an ostrich and say that's an ostrich, here I've now turned the sentence into a picture, and I want it to say, ooh, that's a story, or ooh, that's a Marshall. So I'm going to do the same thing with the test data. And then what I need to do is a little mini neural network that classifies pictures. And really, this is overly simple, but it's going to do a decent job, as it turns out. So here's our network that's going to take our picture and decide that's a Marshall picture or a story picture. I'm going to train our neural network, and I'm going to see how to do. Here's data it's never seen before, test embeddings, and I'm now going to see how well does it do. And it gets it right 76% of the time, which is about 52% better than we would expect if it were just randomly guessing. So now that we know for each sentence it has about a 76% free throw average, as it were, let's see how it does on Martin versus Hunter's Lessee. All right, snarf up Martin, break it into sentences, run BERT on all the sentences, or the words of the sentences in order to turn them into pictures, and now run our little mini neural net on Martin versus Hunter's Lessee, and it seems to think 416 of the sentences were written by Story, 224 were written by Marshall. So does that mean that Marshall wrote 224? Or are those the sentences that the classifiers simply got wrong and they were all written by Justice Story? Right now, I'd say this experiment isn't good enough to calumny Justice Marshall and say that he unethically wrote Martin versus Hunter's Lessee after he'd formally recused himself, but it's interesting. And my main point here is to show you how computational linguistics can help resolve issues of document authenticity, which is certainly a major issue in the modern world, not just document authenticity, but all sorts of forms of work, musical work, artistic work, etc. New topic, networks. And the type of networks I'm talking about here do have some distant relationship to neural networks, but really I'm not talking about neural networks, except it's a little confusing because I have to speak about them briefly. Remember I told you that you can have a neural network that figures out what an image is, okay? So imagine a neural network that has the horrifying job of watching TV series, although this time it's rewarded. As you'll see, it gets to watch a good one. And it says that character A and character B are connected if character E speaks directly after character B, or character A speaks about character B, or character C speaks about character A and character B, or character A and character B are mentioned the same stage direction. That you could only do if you had the script, or they simply appear in a, quote, scene together, which would require the machine to have some notion of what constitutes a scene. But anyway, probably doable. And so suppose you have a computer that knows nothing about Game of Thrones, and we want to find out what can it understand about Game of Thrones. It's sort of a Martian coming down, getting to watch the television series. There's a whole other set of data on the books, but this is on the TV series. And for those of you who don't think this is about law, just instead of character, put citation or case. And suddenly, we might get some very important insights about the relationship of various cases. And there's a very good project lurking in here. Okay, so let's snarf up the data that someone named Matt Beveridge has, or I guess maybe it's Matt H. Beveridge, I don't know who the guy is, but he spent a lot of time watching Game of Thrones and has lots of data. If you know the show, you'll this will make sense to you, but just accept that there are lots of characters in the show, and there ended up being, 8 seasons of Game of Thrones? So we go to the very end. Okay, so one thing we can do is just see who are the most connected characters. So we'll run that code, and we're going to see that Daenerys and Jorah are the most tightly connected, which, if you have watched the show, as I have, makes complete sense. Tyrion and Varys are together. Cersei and her sometimes husband, and also her brother Jaime, are together. And it goes down from there. And I will say that this makes complete sense, like Sam and Gilly and Jaime and Brienne. These are all parts of the show. And without knowing anything about the show in some sense, our little network algorithm has been able to detect that. So we could also have the fun thing of seeing how does the relationships evolve over time. And you can see, well, in season 1, Ned and Robert are all together. Those of you, there's season 2. There are also scenes of them together, although you're going to see that not too many new scenes with them appear together. Those of you who have watched the show will be able to figure out why that is. And you can see sort of the stock of various relationships go up and down, like the dreadful romance between Shay and Tyrion is in season 3, but really that's going to kind of fade away as we move through the show. And we're going to see, things like the Arya-Jaqen relationship grow, etc. Okay, so that's one thing we can do. We can also try to have a visualization of the network and see if we can learn anything by that. And it's just a pretty big jumble of things. Let's see, though, who are the most important characters in the show. And we're going to use 2 different ranking systems. But again, we don't know anything about the show. We don't know anything about the meaning of the show. We're just looking at the connectivity data. So I'm going to write a little function here called character centralities. It's going to figure out the centralities of various characters. And now I'm going to use Wolfram language visualization capabilities to make a plot of this. And we can see that there seems to be a pretty tight correlation between these 2 different centrality measures of eigenvector centrality on the y-axis and PageRank centrality on the x-axis. PageRank, by the way, is the algorithm that really got Google famous and made Google a lot of money. It's gone beyond that now, but this is the algorithm that launched whatever it is, $1 trillion company. Maybe some of you will come up with an algorithm in this class and remember fondly your old Analytic Methods professor. Anyway, we can look at the leading characters according to this network centrality measure, and you can see it's Tyrion the dwarf, Sansa, Jon, Arya, Jaime, Cersei, Daenerys, etc. And I'm just looking at this. Yeah, no wonder some people didn't like the ending. There's a major character who comes out very prominent in the end who doesn't seem to be listed here. All right, I thought the ending was fine. In any event, one other thing we can do is to see if there are communities, that is, if there are people who tend to interact a lot with each other, but tend not to interact with other people. And so we're going to run the high-level function find graph communities. And then we're going to plot that and see, we seem to have one community. I've just taken the top 10 people, if there are up to 10. So we've got the Tyrion, Sansa, Jaime, Cersei, Theon, Ned, the Hound group. Okay, we've got the Northerners, Jon, Sam, Davos, Bran, Tormund, etc. We've got those Starks, Northerners, Robb, Catelyn, Roose, We've got the Daenerys' gang, Daenerys, Jorah, Drogo, Dario, who I didn't think was a very good actor, Sharo, etc. We've got Arya's group, Arya, Jaqen, Thoros, and then some other people. Really, Arya's kind of her own group there. And then we've got a few people who don't fit in very well, and I don't even know who Mully, Blackjack, and Kegs are, and the computer didn't either, and it just sort of stuck them, as you'll see, in its own group. And here's a picture, and it is a coincidence, but there are, famously 7 kingdoms in the Game of Thrones world, and there are 1, 2, 3, 4, 5, 6, 7 communities. But really, that just is it just is a coincidence, but cool. So there's a concept called K-cores, which says that you only get to be in a K-core if you're connected in some way to a certain number of people who are also in the K-core. So everyone in the K-core is tightly connected to each other, and so this forms a pretty complex web of relationships, and we can see it's Daenerys and Jorah and Jon Stark and Sam and Varys, etc. And we can make a little picture of it. Okay. So that is some of the stuff we're going to learn about networks, and I hope you can see immediately the application to law in that what we study. In some sense, it's citation networks and relationships of ideas, and that's what network science is about. Finally, we are going to talk about finance in this class, and my hope is that you'll actually find this useful in your personal life and in understanding some financial issues that maybe your clients have. So here's our problem. Supposing we've got Robin, age 25, and she wants to save a constant fraction f of her income each year so that by age 65, she can purchase an annuity that'll give her an income of $100,000 per year for 30 years before it runs out. Of course, if she lives longer than that, she's in deep trouble. And if she lives for a shorter period, then she'll just give the rest of the annuity to her charity. We're going to assume that throughout this whole period, she can earn 5% in the market. And we're going to assume that she thinks her income over time is modeled by this cubic. Don't concern yourself with how on earth I figured this out or where it came from. But if we want to plot this. We'll let X go. Let's see, she's 25 now, and she's got to make it till she's 65. So that's her income trajectory, and I don't like that at all. Ah, yes, this is the problem. Okay, right. She's 25 now, so she only earns money for 40 years. So now it looks fine. That's a plausible income stream. Okay. Let's solve an equation. Let's use a little algebra, and we're going to say that the time value of the annuity that she gets paid has to be equal to the time value. Sometimes time value is called present value or future value. The time value of the annuity she pays in, that is some fraction k of her income over those 40 years. Don't worry about the particulars here. All you should be thinking about is, wow, this is a complicated financial problem, and it seems to be soluble in one line of relatively simple code. And the answer is that Robin needs to be saving 9.7% of her pre-tax income each year if she wants to meet this goal. So be thrifty. By the way, if you're thinking that seems like a very high premium, it is, but that's because the assumption about when you're going to die is unrealistic here. So the answer is correct, but I've simplified the problem. All right, last thing, portfolio theory. So I've swiped this example, or adapted it, I should say, from the Wolfram language documentation, which is very extensive, and you should just know that what I'm about to do in, 10 lines of code got Harry Markowitz a Nobel Prize for thinking up this stuff in the 1950s. So we've come a long way. All right, so what we're going to do is we're going to retrieve the price of Lockheed stock over this interval. And Berkshire Hathaway, that's Warren Buffett's holding company. Verizon, our favorite cell phone company. Procter & Gamble, I don't know what, they make consumer products, soaps and diapers. We got Walmart, and I threw in something from the banking sector. So I did Bank of America. All right, so let's put together a little portfolio of time series, and what we've got now are these containers, these objects, that hold lots of information about the daily return, I should say, on these various stocks over this period of time. So supposing I want to compute the mean annualized daily return of these stocks, I can do that, and you can see they're getting about 4% over this time period, except for the two latter ones. What are those? Those are Walmart and Procter & Gamble. Those did particularly well. I'm going to compute something called the covariance, which basically says, when Walmart goes up, does Procter & Gamble go up? Does it go down? What about if Walmart goes up? Does that mean Bank of America goes down? And so we're going to compute the covariance matrix here. By the way, what I managed to do here in, a second or so in a line of code, trust me, 10 years ago or in other languages, that's a day's project. All right. So I'm going to compute the return, which depends on, do I have all my money in Walmart, in which case I might have done pretty well, or did I invest it, which stock didn't do so well? 3.2, what was that? That was Berkshire Hathaway. Well, I'm sure he was very prudent. All right, so I'm going to get a symbolic return. I'm going to compute the risk. Don't worry about what these dots are, we'll learn. I'm going to write a function that basically says what I care about is return, but I don't like risk. I don't like when it goes up and down. And so I'm going to subtract off the risk level multiplied by some risk preference or risk hatred coefficient alpha. All right. I am going to, let's fix that right now. I'm going to put some constraints on my portfolio. I'm going to say no shorting is permitted, and so therefore the amount I invest in every stock has to be a positive number, and the total, this is all of my portfolio. I can't invest more than I have. So let's add in those weight constraints. And now, this is what Markowitz basically got his prize for. We've got a pretty fancy function called Quadratic Optimization, which is going to figure out for each level of risk hatred alpha what the optimal portfolio looks like in order to maximize this return less risk. So I'm going to compute that, and that's the Nobel Prize right there. Now let's actually make a frontier. Let's actually come up with, what if I just invested randomly? What if I just threw money at the stock market? And we can now compare this optimal line with what would happen if I invested randomly. And you can see that actually random investing, at least according to this theory, you actually don't do as well, and you might needlessly sacrifice risk or return. We could actually look at, hey, what stock does this actually mean? And as I increase my hatred of risk, if I don't care too much about risk, I basically want to put most of the money in Procter & Gamble and the rest in Walmart, because those were the two stocks that did the best. But if I want to avoid risk, I want a more diversified portfolio, and so actually then I want to shrink my P&G holdings. I want to get boring old Verizon in the portfolio. I want to keep some Walmart. What else? I guess I still want to keep a good chunk of Walmart, and have a little Berkshire Hathaway and a little Lockheed in the mix. And you can see actually how does my changing the risk aversion parameter change the level of return I get. So if I'm willing to take some risk, I can get on balance 7.5%. If I'm not willing to take some risk, I can get about 5%. Since Markowitz did his work, there have been all sorts of concerns about whether this is valid, and the fact that we're looking retrospectively doesn't mean that these levels of return are going to persist or that the covariance between the stocks is going to remain. So this is not intended as a practical investment tool, but it's sort of pointing towards how you might mathematically start to think about these questions. So at the beginning of this video, remember that ages ago, I warned you it was a little scary, but I hope it's exciting, and I want you to have faith in yourself. And I sort of wonder if I'm here like the CrossFit trainer who is showing you those photos of people with well-developed physiques and telling you the new recruit with a little, soft abdomen and flabby the rest, that actually you could look like that too. And many people don't believe them, or they think that they're too old or fat or clumsy or lazy to get there. And so I'm not going to say that at the end of this course you're going to be the mathematical computational law equivalent of Matthew Fraser or Tia Claire Toomey. And you're going to sweat along the way, no doubt about that. But I'm going to be there to hold your hand, provide some guidance and encouragement, and I hope make it fun.